Somewhere in a hospital in a northern European city, a nurse carries a small sealed container down a corridor. Inside it is a liquid. The total amount of the active substance in that liquid weighs less than a grain of dust, less than what stays on your fingertip when you touch a dirty surface. And that substance, that almost nothing, is about to be injected into a patient whose cancer has already survived 2 rounds of chemotherapy. Here is the part that stops me every time I think about it. That substance does not exist anywhere on Earth in any meaningful quantity. You cannot mine it, you cannot refine it, you cannot store it. The entire planet, every mountain, every ocean floor, every cubic kilometer of rock from the surface down to the deepest geological layers contains less than a few dozen grams of it at any given moment. And those grams are not sitting still. They are constantly being born and constantly dying, replaced by new atoms that will also be gone within hours. What the nurse is carrying was created that same morning in a particle accelerator located in the same city. Because if it had been made anywhere farther away, it would have largely ceased to exist before reaching the patient. We are talking about element number 85. An element so strange, so boundary-breaking, and so cosmically rare that most working chemists will go their entire careers without ever being in the same room with even a single visible trace of it. And the deeper you go into its story, the more it starts to feel less like chemistry and more like something else entirely. Something that should not be possible, but somehow is. Before we get to that hospital room and what happens inside it, we need to go somewhere else first. We need to go to the periodic table, and specifically to one of the most uncomfortable neighborhoods in it. Because element 85 did not arrive quietly. It arrived after decades of wrong turns, embarrassing mistakes, and at least 4 separate scientists who were absolutely certain they had found it, announced it to the world, and then had to watch their discovery fall apart in front of everyone. But even before those failures, there was a man who pointed at an empty space in a chart and said, "Something lives here. I just cannot see it yet." And almost nobody believed him. Friends, if you find this kind of story as fascinating as I do, subscribe and leave a like. It genuinely helps this channel keep going and means more stories like this one. Now picture the periodic table not as a poster on a classroom wall, but as a family. A large, messy, very specific family where everyone follows the rules of the household almost without exception. The Halogen group is one of the tightest clans in that family. 7 members, stacked vertically, and every single one of them follows the same pattern as you move from top to bottom. They get heavier. Their color deepens, their boiling points climb, their aggression fades. The one at the very top is a pale, nearly invisible gas that corrodes steel and eats through glass. The next one down is a yellow-green cloud that was used to cause mass casualties in the trenches of the First World War. The one after that is a dark, reddish-brown liquid, one of only 2 elements that sit as liquids at room temperature, and it burns skin on contact. Then comes a dark purple crystalline solid with a sharp medicinal smell that most people recognize from antiseptic bottles. So by the time you reach the bottom of this column, the pattern is absolutely clear. The next member should be even darker, even heavier, even less aggressive, even more sluggish. A kind of extreme iodine. That is what every textbook logic, every chemical trend, every reasonable expectation would predict. Instead, element 85 does something that should be impossible for a halogen. Under certain chemical conditions, it gives away electrons rather than taking them. It forms positive ions. It behaves like a metal. Under other conditions, it flips completely and acts exactly like its halogen siblings. It sits at the exact boundary between 2 worlds and refuses to belong fully to either of them. Some chemists call it a metalloid. Some call it a pseudohalogen. Some just call it deeply inconvenient for anyone who likes clean categories. The reason for this identity crisis goes all the way down to physics. Inside the nucleus of element 85, there are 85 protons, And that enormous positive charge forces the innermost electrons to orbit so fast that they reach speeds approaching half the speed of light. At that speed, according to the rules Einstein wrote down, those electrons become measurably heavier than standard atomic models predict. Their orbits compress inward. That compression changes the behavior of every electron shell above them, cascading outward until the chemistry of the whole atom is altered in ways that simpler elements simply do not experience. Gold is yellow instead of silver-white for exactly this reason. Mercury is liquid at room temperature for exactly this reason. And element 85 refuses to be either a proper metal or a proper nonmetal for exactly this reason. Relativistic physics, baked into the structure of the atom itself, blurs the line until the line disappears. And here is where the story takes its first sharp turn. Because while all of this makes element 85 chemically fascinating, there is another property of this element that makes it unlike anything else in the known universe. A property that has nothing to do with its electron shell and everything to do with the heart of its nucleus. And that property is why, for decades, every scientist who went looking for it came back empty-handed. A scientist once stood in front of his colleagues and pointed at an empty space on a chart, and the room laughed at him. Not politely, not with the kind of restrained academic skepticism that gets written up in journals. They laughed the way people laugh when someone says something they consider genuinely absurd. And the man who was laughed at did not argue back. He did not raise his voice or wave his hands. He simply picked up a pen and wrote down a list of properties for the thing he claimed was hiding in that empty space. Density, color, reactivity, the kinds of compounds it would form, the way it would behave when heated. He wrote it all down with the calm of someone who was not guessing, but remembering something he had not yet been allowed to see. That moment happened in the second half of the 19th century, when the scientific world was still arguing about whether atoms even existed in any real physical sense. A chemist named Victor Hess, working in a mid-sized European university with drafty lecture halls and ink-stained wooden desks, had spent years mapping the relationships between known elements, not just cataloging them the way others had done before him, but listening for the pattern underneath. Because there was a pattern. Every element seemed to echo the ones above and below it in a way that was too consistent to be random. And if the pattern was real, then the gaps in it were not empty. They were occupied by things that had not been found yet. Hess did not just leave the gap at position 85 open. He described what was in it. He said it would be heavier than iodine, darker, less reactive than its neighbors, but more metallic in character. He said it would form compounds similar to iodine, but with a different edge to its behavior. His colleagues called this philosophy, not chemistry. One senior professor at a conference in Leipzig reportedly said that predicting undiscovered elements was no more scientific than reading tea leaves. Hess went home and kept working. And then, one by one, the gaps began to close. An element he had predicted with a density of roughly 6 grams per cubic centimeter was discovered by a French chemist analyzing ore samples, and its measured density came back at just over 6. Another predicted element turned up in a Scandinavian mineral, and its properties matched the written description almost exactly. Then a third. The room stopped laughing. But position 85 stayed empty. Years passed. Then decades. The man who had pointed at that gap died without seeing it filled. And by the time the 20th century arrived and physics began tearing apart the very concept of what an atom was, the empty cell had become something of an obsession. A wound in the table that refused to heal. And what nobody yet understood was that the reason it refused to heal had nothing to do with how hard people were looking. It had to do with something far more fundamental, something that made the search itself almost meaningless from the start. That something became brutally clear only after a string of failures so embarrassing that several of the scientists involved spent years trying to quietly distance themselves from their own published work. And the first of those failures came from a man who genuinely believed he had cracked the problem with a device of his own invention. His name was Leonard Faro, and he worked at a technical institute in the American South in the early part of the 20th century. Faro had developed what he called a magneto-optical rotation method. The idea was elegant on paper. Every element, he claimed, rotates polarized light by a specific angle when dissolved in solution and placed inside a magnetic field. If you introduced an unknown element into the mixture, the angle would shift in a way that identified it uniquely. Faro had spent years refining the device, and he was convinced it worked. He was so convinced that when he began studying samples of heavy mineral sand from South America, and the device showed anomalous readings, he did not question the instrument. He questioned the periodic table instead. He announced that he had found element 85. He gave it a name. He published. He accepted congratulations. And then two independent laboratories, one on the East Coast and one in California, tried to reproduce the result and got nothing. Absolutely nothing. When they examined Faro's device more carefully, the problem became obvious. The instrument was so sensitive to external interference that it was essentially recording the temperature of the room, the vibration of passing vehicles outside, the humidity in the air. It was not measuring elements. It was measuring its own surroundings and producing signals that looked like data, but were not. Faro had fallen into one of the oldest traps in experimental science. He already knew what he was looking for, and so his brain, like every human brain, found it. This is not a flaw unique to Faro. It is something every scientist, every doctor, every detective, every judge has to actively fight against every single day. The mind is a pattern recognition engine, and it does not switch off just because you are wearing a lab coat. And what makes this particular story worse is that Faro was not the last. After him came a Romanian physicist who used X-ray spectral lines and named his discovery after a word meaning longing in his native language. After him came an Indian chemist who had confused the unusual behavior of bismuth under irradiation for a new element entirely. After him came a Swiss researcher who made the same mistake twice, published twice, and was wrong twice. 4 separate announcements, 4 separate names, 4 separate moments of apparent triumph. And every single one collapsed under scrutiny. The empty cell at position 85 seemed almost to be mocking the entire field. But here is what none of these men understood, and what would only become clear much later. They were not failing because their methods were too crude or their instruments too weak. They were failing because the thing they were looking for was physically incapable of sitting still long enough to be found by anyone searching in minerals and ores. The truth of why that was the case would require a completely different kind of thinking. And it would take a woman working alone in an occupied city in a half-empty institute with no international contacts and dwindling supplies to finally see it. While 4 men were busy announcing discoveries that did not exist, a woman in Vienna was quietly doing the work that actually mattered. Her name was Elena Dorn, and she had been at the Radium Institute for over a decade by the time the political situation in Central Europe began to collapse. She was not famous. She did not have a professorship. She had a desk near a window that let in cold drafts in winter, a set of detection instruments that she had partially repaired herself using spare parts ordered from 3 different countries, and an almost obsessive focus on the decay products of heavy radioactive elements. When the annexation came and the atmosphere in the city changed overnight, the institute began to empty. Senior colleagues left in a matter of weeks. Some gave her a handshake at the door. Some left without saying anything at all. The supply of certain reagents stopped arriving. Letters to foreign laboratories went unanswered. The institute, which had once hummed with the sound of collaborative work, the clinking of glass, the low murmur of people talking through problems together, went almost completely silent. Dorn stayed, not because she had nowhere to go, but because she was in the middle of something. She had been tracking the behavior of particles emitted during the decay of uranium compounds, specifically looking at the full chain of products that uranium breaks down into over time, and she kept finding signals she could not account for. Not strong signals, not the kind of dramatic readings that Farrow had mistaken for discovery. Quiet ones. Brief flashes of alpha radiation appearing and disappearing in the decay chain at moments where no known element should have been producing them. She noted them carefully, cross-referenced them against every published decay table she had access to, and sat with the question for months. What she eventually concluded was something that reframed the entire search. She was not looking at a stable element hiding in uranium ore. She was looking at an intermediate step in the decay process itself. A momentary product born from one element, lasting for a fragment of time, then transforming into something else. She confirmed the presence of two distinct forms of element 85 in the natural decay chain of uranium. Not synthesized, not extracted, simply passing through, the way a sound passes through a room. There one moment, gone the next. And in the same set of papers, she methodically dismantled the work of the Swiss researcher who had preceded her, showing precisely which known decay products he had misidentified and exactly why his instruments had produced the readings he had interpreted as a new element. She did this without drama and without apparent satisfaction. She simply corrected the record. Years later, after the political crisis had ended and the Institute slowly began to function again, Elena Dorn was appointed the first female full professor in the history of the university, an institution that had been operating for over 500 years before it made that decision. What she had found, those fleeting signals in the uranium chain, immediately raised a question that nobody had thought to ask before. If element 85 appears and disappears in seconds, how is it that the Earth contains any of it at all? The answer to that question is one of the most quietly astonishing things in all of chemistry, and we will get to it. But first, there is another part of this story that runs parallel to Dorn's discovery, one that starts not in a European institute, but in a California laboratory, and involves a machine that looked less like scientific equipment and more like something out of an industrial nightmare. The man standing in front of it had dark circles under his eyes and had not slept properly in 2 days. His name was Anton Vasek, and he was a physicist who had already helped create one synthetic element before arriving at the Berkeley laboratory in the late 1930s. He had left his position in Europe under circumstances that were not his choice. Racial laws had taken his professorship. He had a wife and a young child, and a temporary contract that paid significantly less than his American colleagues received for equivalent work. He kept a photograph of his university office on his desk, not out of nostalgia, but as a reminder of exactly what kind of world produced the situation he was now in. The machine he was working with was a cyclotron, a particle accelerator that worked not by pushing particles in a straight line, which would have required a structure kilometers long, but by spinning them in an expanding spiral. 2 curved electrodes, shaped like the letter D, sat inside a chamber between the poles of an enormous magnet. Each time a charged particle crossed from one electrode to the other, an alternating electric field gave it another push. The magnet kept bending its path into a curve. So instead of flying straight, the particles spiraled outward, gaining speed with every revolution, until by the time it reached the edge of the chamber, it was moving fast enough to do something remarkable. It could break through the electromagnetic barrier surrounding another atomic nucleus and merge with it. Vasek and his 2 colleagues, a physicist named Gregor Teller and a young researcher named Paul Shin, loaded a target of pure bismuth into the vacuum chamber. Bismuth sits at position 83 on the periodic table. Add 2 protons to its nucleus, and the charge becomes 85. An alpha particle, the nucleus of a helium atom, carries exactly 2 protons and 2 neutrons. The math was clean. The execution was anything but. For several hours, a stream of alpha particles accelerated to an energy of nearly 30 million electron volts hammered into the bismuth plate. When the bombardment ended and the team brought their detectors close to the target, the instruments immediately registered alpha radiation that did not belong to bismuth, did not belong to polonium, did not match any element in any reference table they had. Chemical tests confirmed it was volatile when heated and was extracted by organic solvents in the same way iodine would be, but the radiation signature was entirely its own. They had made element 85 in a machine, atom by atom, for the first time in history. They published their results and named it, drawing on an ancient Greek word meaning unstable and fickle, a name that fits so perfectly it was almost uncomfortable. And then, before anyone could fully absorb what had just happened, the world intervened. The cyclotron was repurposed. The research was set aside, and Vashik himself was pulled into a project so secret and so consequential that his work on element 85 would not be revisited for nearly a decade. What he discovered on that other project, far from California, in the desert, would change the nature of that secret program in ways nobody had anticipated. Here is the thing that nobody tells you when they explain the periodic table in school. The reason element 85 cannot exist in stable form has nothing to do with chemistry at all. It has to do with a war happening inside every single nucleus. A war that has been going on since the first atoms formed in the universe. And at 85 protons, that war is unwinnable by design. Let me explain what I mean. Inside any atomic nucleus, 2 forces are fighting each other constantly. The first one is the strong nuclear force, and it does exactly what its name suggests. It grabs every particle in the nucleus, every proton and every neutron, and pulls them together with enormous strength. The catch is that it only works at extremely short range. We are talking about distances so small that the word tiny does not come close to describing them. A few femtometers. A femtometer is 1/1,000,000th of 1 nanometer. That is how short the reach of this force is. The second force is electromagnetic repulsion. Every proton in the nucleus carries a positive charge, and positive charges push away from each other. Unlike the strong force, this repulsion does not care about distance. It works across the entire nucleus and beyond. So here is the situation. You have one force that pulls everything together but only works up close, and another force that pushes protons apart and works at any distance. For small nuclei, the pulling force wins easily. But as nuclei grow larger, as you add more and more protons, the total repulsion grows faster than the pulling force can compensate. Neutrons help because they contribute to the pulling force without adding any charge. This is why heavy stable nuclei contain more neutrons than protons. They are essentially using neutrons as a buffer against the growing electromagnetic pressure. But even that strategy has limits. And here is where the concept of magic numbers becomes important. Certain specific counts of protons or neutrons create a kind of structural perfection inside the nucleus, a configuration so well balanced that it resists decay far better than its neighbors. These numbers are 2, 8, 20, 28, 50, 82, and 126. The nucleus of lead with 82 protons and 126 neutrons contains 2 magic numbers simultaneously. It is the endpoint of multiple radioactive decay chains. There is simply nowhere more stable for it to go. 85 is not a magic number. It sits between 2 of them and satisfies neither. Any nucleus built around 85 protons will always be trying to shed that excess charge, either by spitting out an alpha particle, which reduces the proton count by 2, or by pulling in one of its own electrons, which converts a proton into a neutron and drops the charge by 1. There is no isotope, no combination of neutrons, no configuration that makes 85 protons stable. It is not a gap in our knowledge, it is a boundary written into physics itself. And layered on top of all of this is the relativistic effect we talked about earlier. Those compressed electron orbits that blur the element's chemical identity. The same enormous nuclear charge that makes the element chemically strange also makes it structurally doomed. The two things are connected at the root. 85 is not an element that is hard to find. It is an element that the universe actively prevents from accumulating. And once Voshik and his colleagues understood this fully, after the war ended and the research resumed, a completely different question emerged. Not how do we find this element, but what do we do with it now that we can make it? The answer to that question started not in a physics laboratory, but in an oncology ward, and it began with a problem that had been frustrating cancer researchers for decades. Here is the brutal reality of treating cancer that is spread through the body. By the time individual cancer cells have broken away from a primary tumor and scattered through the bloodstream, lodging themselves in distant tissues in clusters so small they are invisible on any scan, the standard tools of treatment become almost useless. Conventional radiation, the kind used in external beam therapy, fires energy into the body from outside. It is powerful but imprecise. It damages cancer cells, but it also damages every healthy cell between the source and the target. And the range of that damage is measured in centimeters. Chemotherapy drugs circulate through the entire body and affect any cell that divides quickly, which is why patients lose their hair and experience damage to the gut lining. These are not side effects in the trivial sense. They are direct consequences of the fact that the treatment cannot tell the difference between a cancer cell and a healthy one with any real precision. The idea that changed everything was simple in principle and ferociously difficult in practice. What if instead of firing radiation at the body from outside, you delivered the radioactive source directly to the cancer cell, from the inside, and made the radiation so short-ranged that it could not reach beyond the cell it was targeting? Alpha particles are perfect for this in theory. They are heavy. They carry a double positive charge. When they travel through biological tissue, they tear through molecules like a hot wire through wax, creating a dense trail of damage. But they stop within 40 to 80 micrometers, less than the width of a few cells. Every bit of their energy is spent within that tiny range. A cancer cell hit by an alpha particle from inside receives dozens of simultaneous breaks in its DNA, far more than any cellular repair system can handle. The cell cannot divide. It cannot spread. It cannot evolve resistance the way it can against drugs, because you cannot evolve resistance against physics. The challenge was finding an alpha emitter that could actually be delivered to cancer cells with enough precision to make the therapy work. Several candidates were tested. One had a half-life of 10 days, which sounds convenient until you realize that as it decays, it produces a chain of radioactive daughter products that break free from whatever molecule they were attached to and migrate through the body, accumulating in organs where they were never intended to go. Another emitter was chemically too inert to attach reliably to the biological carrier molecules needed for targeting. Element 85, specifically its form with a mass of 211, avoided both of these problems in a way that seemed almost designed for the purpose. Its half-life of just over 7 hours is short enough that it decays quickly and leaves no long-lived radioactive products behind, but long enough to allow a complete synthesis and delivery cycle within a single working day. Its decay produces 2 alpha strikes in rapid succession and then ends at stable lead. No radioactive chain, no migrating daughter products. And its chemical similarity to iodine meant that decades of existing research into how to attach radioactive iodine to targeting molecules could be adapted and applied almost directly. The question was no longer whether element 85 could theoretically work as a cancer treatment. The question was whether anyone could actually build the infrastructure to make and deliver it fast enough to matter. Every atom of gold in every piece of jewelry ever made has existed since before the Earth was born. But every single atom of element 85 that exists right now, anywhere on this planet, was created within the last few hours. And every atom that existed this morning is already gone. That fact alone should stop you completely, because it means we are not talking about a substance in any conventional sense. We are talking about a process wearing the mask of a substance. To understand where it comes from, we need to leave the Earth entirely and go back to the very beginning. The Big Bang produced hydrogen, helium, and almost nothing else. No carbon, no iron, no gold, no uranium. Everything heavier than those first two elements had to be built later, inside stars, through nuclear fusion reactions that took millions and billions of years. Stars are nuclear furnaces, and they burn through a sequence of fuels in order of increasing difficulty. Hydrogen first, then helium, then carbon, neon, oxygen, silicon, each stage burning hotter and faster than the last. But this process hits a wall at iron. Fusing elements lighter than iron releases energy, and that released energy is what holds a star up against its own gravity. Fusing anything heavier than iron costs energy instead of releasing it. So when an iron core builds up in the center of a massive star, the energy source cuts off. The core collapses in less than a second. The outer layers fall inward, hit the suddenly rigid core, and bounce outward in a catastrophic explosion that for a brief moment outshines an entire galaxy. This is a supernova, and for a long time, astrophysicists believed that supernovae produced all the heavy elements in the universe. Then they started measuring. The actual abundance of gold, platinum, and uranium in galaxies was significantly higher than supernovae could account for. Something else was making heavy elements, something far more violent and far rarer. That something turned out to be neutron star mergers. A neutron star is what remains after a supernova strips away everything except the core. It is a sphere roughly 20 kilometers across, containing more mass than our entire sun, packed so tightly that a single teaspoon of its material would weigh roughly 1 billion tons on Earth. The matter inside is almost pure neutrons, pressed together so hard they are essentially touching. When two of these objects orbit each other in a binary system, they lose energy slowly over billions of years and spiral inward. In the final seconds before contact, they are moving at a significant fraction of the speed of light. The collision lasts milliseconds. In that collision, conditions exist that cannot be replicated anywhere else in the universe. Neutron densities so extreme that atomic nuclei absorb dozens of neutrons in rapid succession, building up to masses far beyond anything that can exist stably, then cascading back down through a rapid series of decays that produce the full range of heavy elements in seconds. Gold, platinum, uranium, and element 85. A single such merger can produce several times the mass of the Earth in heavy elements alone. The evidence for this was locked inside a gravitational wave signal detected by an observatory using laser beams to measure distance changes smaller than the diameter of a proton, a signal that came from a merger that happened over 100 million light-years away. When telescopes turned to the location and captured the fading light of the aftermath, spectral analysis showed heavy elements being created in real time. For the first time in history, the origin of gold was not a theory, it was an observation. And element 85 was there too, in that cloud, being born in one of the most violent events the universe produces. But it did not survive the journey. Its half-life is measured in hours. The cloud that carried it cooled and dispersed over thousands of years. Element 85 was dead long before a single molecule of water formed in the nebula that eventually became our solar system. So here we are, back in that hospital corridor, back to the nurse carrying the small sealed container with almost nothing inside it. Now you know what that almost nothing actually is, and the story of how it got there is not a short one. It was synthesized that same morning in a cyclotron located somewhere in the same city, because the 7-hour half-life leaves no margin for long-distance transport. By the time the container reaches the patient, a measurable fraction of the medicine has already decayed into bismuth and ceased to exist as element 85. The clock starts the moment the bombardment of the bismuth target ends, and it does not pause for traffic, for paperwork, or for anything else. The team that makes it works under conditions that most laboratory chemists never encounter. The irradiated target is intensely radioactive and must be handled entirely by remote manipulators behind thick shielding. The element is driven off the target by heating it in a stream of inert gas collected in a cold trap, and then attached to a carrier molecule, a specially designed antibody or a targeting compound that has been engineered to seek out a specific type of cancer cell and bind to its surface. The bond between the carrier and the element must be strong enough to survive the journey through the bloodstream without releasing element 85 in the wrong location, because free element 85 in the body behaves like iodine and heads straight for the thyroid gland. The chemistry of that bond is still being refined by research groups across several countries. When the carrier finds its target cell and attaches to its surface, element 85 fires its alpha particle at a range of effectively 0. The DNA of that cell receives damage that no repair system can fix. The cell stops dividing. It does not need to be destroyed outright. It simply needs to lose the ability to reproduce, and that is enough. In scattered peritoneal cancers, where malignant cells coat the inner surfaces of the abdominal cavity in a thin layer that surgery cannot fully reach, the carrier molecules are introduced directly into the cavity and allowed to find every cell on their own. In certain thyroid cancers, the natural affinity of the element for iodine-absorbing tissue is used deliberately. The same logic as iodine therapy, but with a striking range of only a few cell widths instead of several millimeters. Clinical trials across Scandinavia, North America, and East Asia are producing results that researchers describe with a kind of careful excitement, the tone of people who have seen enough promising things fail to let themselves celebrate too early, but who are also clearly looking at something real. The infrastructure required to make this work at scale is the final barrier. A cyclotron capable of producing element 85 must be within an hour or two of the clinic where treatment is delivered. There are hundreds of medical cyclotrons in the world, but most are not equipped for this specific process. Building that network is the work of the coming decades. And here is what strikes me most about this entire story, from the empty cell in a 19th century table to the sealed container in a hospital corridor. The thing that makes element 85 medically extraordinary is precisely the thing that makes it cosmically rare. Its instability is not a flaw that scientists are working around. It is the mechanism. The fact that it decays so quickly, so completely, and with such precision is exactly why it can destroy a single cancer cell without touching the one next to it. The universe spent billions of years building something that only exists for hours, forged it in the most violent collision imaginable, embedded it as a fleeting shadow inside radioactive decay chains. And it turned out to be one of the most targeted tools medicine has ever found. Not despite its brevity, because of it. Some things do not need to last in order to matter. They just need to arrive at exactly the right place at exactly the right time. Here is the question I want you to sit with, and I genuinely want to read your answer in the comments. If an element that exists for only a few hours can leave a permanent mark on a human life, what does that say about the things we dismiss as too small, too brief, or too rare to make a difference? Think about that and tell me what you think below. If this story made you see the periodic table differently, leave a like and subscribe to the channel. There is a lot more where this came from.